Hello and welcome back to the ASC video series. I'm Dr. Sean Perry. This is Introduction to Statistics, STA 2023. We're looking at a problem or collection of problems from Chapter 8 on confidence intervals. So before we begin, let's discuss the function of a confidence interval. You take a sample to try to figure out what the population mean is. So your sample will have a mean of x bar, and that forms a guess as to what mu, the population mean, might be. When we know the standard deviation of the population, we can be a bit more precise. We will add and subtract to our estimate of x bar some buffer, give or take a certain amount, and we will be a certain percentage confident, that is to say there's a certain percentage chance that the true mean lies inside of this interval. So this is a plus minus symbol, right? We're going to have two numbers, one lower and one greater, and these will form the endpoints of an interval. Now it's very important to notice that the standard deviation that they use here is that of x bar, that of the sampling distribution. So we're going to have to remember to divide by the square root of n in any one of the confidence intervals that we're going to be constructing. If we don't know sigma, we're going to have to estimate that too. We'll use the standard deviation from our sample that we take, and we'll use that as an estimate for how much wiggle room we should give around our estimate to get a certain degree of confidence. Notice that instead of using z-scores, there was now a t-score to be used. These come from a similarly shaped distribution that is just a little bit wider to account for the fact that we're also estimating sigma and not just mu. In either case, the thing that we're adding and subtracting is called the margin of error. This is the wiggle room that we give ourselves in order to have a certain percentage confidence that the true mean lies in our interval. Now you can prescribe how big a margin of error you want, and there's a certain number of elements that you would have to have in your sample in order to get that wide of a margin of error, given a particular degree of confidence. We'll talk more about how to select z and t-scores in order to give you a certain degree of confidence when we do the problems. But suffice it to say, that is fixed. As soon as you say, oh, I want to be 90% confident that the true mean is in my interval, you know this z. Now, something slightly different than the previous chapters is that we are going to have a different set of equations when we are talking about a proportion. This is when the parameter that we are trying to estimate is given as a percentage of the total population. So they might say that 20% of the population feels a certain way. This would be an indication to use these p variables here. P hat is what that symbol is called, and this is your estimate for the mu, the true mean of the population. Notice that the calculation of sigma of p hat, the standard deviation of the sampling distribution, is given by a slightly different formula. Your p hat is going to be from your sample. Your q hat is going to be 1 minus that. The margin of error is calculated similarly, and the sample size required is also calculated in a similar way. You could take these equations and just resolve them for n to get this formula. So here I have a problem from the homework. It says a marine biologist would like to estimate the mean weight of all kingfish on the Treasure Coast using a 97% confidence interval. The standard deviation of weights of all kingfish is known to be 8.9 pounds. How large a sample of kingfish should the marine biologist select so that the estimate is within 1.31 pounds of the true population mean? Round the solution up to the nearest whole number. So the important data here is that the confidence level, which I'll call C, it needs to be 97%. The standard deviation of the weights of all kingfish, the keyword all here lets us know that we are talking about sigma, the population parameter. This is given as 8.9. How large should the sample be so that the biologist's estimate is within 1.31 pounds? This is giving us our margin of error. It's telling us what amount of wiggle room I need to give around whatever estimate I take to be 97% confident that the true population mean is in there somewhere in that interval. So the question here is really, what is n? What should the sample size be? So let's say that our confidence given by 97%, how do we find z from this. So we should be able to immediately find out what our z-score should be, given the confidence. So let's see how to find that. Essentially, what we are doing is we're looking at a normal distribution, and we're putting 97% in the middle. This leaves 3% to be split into each tail, which is 0.015 in each tail. So from here, we could find out what z-score should put 0.015 in each tail. Well, if I look up inverse norm in my calculator of 0.015, right, it's going to give me this z-score here, which is going to be a negative z-score. If I want the positive z-score, I could then just take the negative of this. This is a one-line input into your calculator that you can use to find z-scores for your confidence interval. Take whatever your confidence is, take it away from 1, and divide it by 2. Put this into inverse norm, and then take the negative, and we'll get our z-score. So let's take a look at that on the calculator. I'm going to go to second, distor, and down to inverse norm. We'll take 0.015 and put it in our tail, and we get negative 2.17. So this value, negative of that, will be 2.17, approximately. So now if we consult our formula sheet, we have the following formula for n. I'll just remark, as far as calculating is concerned, this is no different than taking this fraction and squaring it, which is how I will calculate it. We now have each one of these variables, so we can simply plug them in. This will be 2.17 times 0.9 divided by 1.31, and we square it. Typing that into our calculator, we get 217.34 yada yada yada, and we are always going to want to round that up. We round that up to 218, and there we are. So let's take a look at our next problem. This one, we're actually going to construct two confidence intervals, both at the 99.9% confidence level. One is going to be done using z-scores, and the other will be done using t-scores. So this says, a marine biologist would like to estimate the mean lifespan of all Florida manatees. The mean lifespan of a random sample of 43 manatees was found to be 53 years. The standard deviation of the lifespans of all Florida manatees is known to be 9.9 years. So right off the bat, we can extract some of the information from this. The random sample was taken, and it was of 43 manatees. The mean has been given as 53, and the standard deviation that has been given is that of all Florida manatees, so it is sigma for the population, 9.9. They give us a confidence level of 99.9%, and they want us to give them back a confidence interval with these particular parameters and statistics. The next one they'll look at will have a unknown population standard deviation and a known sample standard deviation, but we'll look at that in just a moment. So let's draw a quick picture to associate a z-score with this confidence level. What they are saying is we have 0.999 in the middle here, and that puts 0.001 split between two tails. That means there's 0.0005 in each tail. Again, how do we calculate our z-score here? We're going to take the negative of the inverse norm of 0.0005. Heading to our calculator, we do second, distor, down to inverse norm. And now we're going to put in an area of 0.0005. And this gives us the associated z-score of 3.29. So again, from the confidence, we're able to immediately get the z-score that we're going to use for this confidence interval. I'll also just remark, our sigma that we want is not the sigma given, but sigma of x bar. And this is going to be the original sigma divided by the square root of n. Now let's recall the formula for our confidence interval, right? X bar plus and minus z times the sigma of x bar. So I'll write those two separately and include the formula for the sigma of x bar. One of the reasons I will do this all as one formula is because this will help us avoid rounding error. And at this point, we have all these parameters. We have x bar, we have z, we have sigma, we have n. So we can just plug it in at this point. So substituting, we get this. And we can type it into the calculator as so. To get the second answer, I'll just go second enter to bring up my last entry and change this minus to a plus. So there's our first one. I'd like to also note at this time, you can do this on the calculator. If we go to Stats, over to Tests, and down to Z interval, we know it's Z because they gave us sigma, and we could put this in either as data in a list or as statistics, which is what we were given. And then they'll prompt us for some of these values, and filling in the information given, we calculate our interval. So in the next part, they left everything the same, but they did change the value of the standard deviation. This might have shown you a little bit more clearly the difference between Z's and T's if they'd left this the same as well and just changed it from sigma to S. Notice that it has itself gotten bigger. Now, a T distribution is already going to widen our interval, and they have now increased the standard deviation as well. So we expect this confidence interval that we're going to calculate to be wider. So again, the main idea here is that nothing else is really changing except for this fellow, who is now S for the sample standard deviation, and this is now 11.1. The idea of how we get our t-score for this is going to be very similar to how we got a z-score in the last one. We're going to imagine that some distribution has 0.999 in the center, which puts 0.0005 in each tail. Now, there is a function on the calculator that sort of doubles for inverse norm, and that's inverse t. Now, this is on the TI-84s, but not on the TI-83s. Not all of them anyway. So I will show how you would do this on a chart for this problem as well. Notice they're asking us for another parameter, the degrees of freedom. The only thing you need to know about degrees of freedom right now is that it's equal to n-1 in this problem. So we're going to put the number 42 here. Again, that's just your sample size minus 1. And this gives us this t-score here, off by a sign, of course. Right, these are going to be my negative t down here and my positive t up here. So knowing that we are dealing with a standard deviation of our sample only, knowing that we are a confidence level of 99.9%, we can now say that t is equal to 3.5377 and so on. If you didn't have this 84 and you couldn't do this with taking negative of inverse t, you would have to go to a table. So here I have a t-chart that I looked up on the internet because the one in the book didn't go down to the right level. We needed only 0.05% in each tail. Scrolling down to a degree of freedom equal to 42, or n-1, we have 3.538 given as the t-score. Again, you can get these directly off of the calculator, but only if you have a 84 or better. But after that, everything goes about the same. We're really looking to use S of x bar, which is going to be S divided by the square root of n. Our confidence interval is going to be given by x bar plus and minus S of x bar times t. Well, we now have t and S of x bar, so this is going to be x bar minus t times S divided by the square root of n, and this is going to be x bar plus that. So now it's just substitution. And typing these into our calculator, we get the following. So here we can see they got a slightly different answer. Let's see if that's not because they used some rounding somewhere by looking at the calculator for the answer directly. And we're going to go down to t interval instead of z interval. Now we're going to still input this from stats. We have an S of x. Now, that's not S of x bar, that's S of x as in the standard deviation of x's, not of x bars. So we're looking at individuals here, and we calculate, and there you have it. So there is a slight discrepancy here, but it's well within tolerance. That's how they get the correct answer, but this is a more precise answer. Probably because they had to use a rounded t value because the table doesn't actually go that far in the book. So now let's look at some proportion type problems. This one says a psychologist would like to estimate the proportion of Americans that say the future of the nation is a significant source of stress for me. To help form an estimate, the psychologist randomly selected 750 Americans and found that 55.6% of the sample agreed with the statement. Using a 95% confidence interval, determine the margin of error E and a confidence interval for the true proportion of all Americans that say the future of the nation is a significant source of stress for me. Report the confidence interval using interval notation. round solutions to 4 decimal places if necessary. So let's read off the important parameters from the problem. You have n equals 750 for this sample, and this gives us a p-hat value, p-hat meaning it's for the sample, of 55.6%, which is 0.556. They want a confidence interval of 95%, or 0.95. Now, when we do proportion problems, we are usually talking about an n very large. When n is large, usually larger than 100 or so, you can instead use a z-score where we might have thought we needed to use a t-score here. We might think that because they didn't tell us anything about the population standard deviation. However, t-scores become z-scores as you take larger and larger sample. One curve morphs into the other one for n large. So we're not going to need to worry about that. We can just go straight to our z-scores. So I'll just skip the picture here and say that z is going to be equal to the inverse norm, or negative the inverse norm, of 1 minus 0.95 divided by 2. You can front load this into the inverse norm this way. That is to say, you can put this formula, 1 minus the confidence level over 2, in for your area and take the negative of that to get 1.9599, yada, yada, yada. So we'll round this to 1.96. Taking a quick glance at our formula sheet, this is the confidence interval formula we're going to be using, and we see it's very similar to the last one. We're adding and subtracting the z-score times some standard deviation of the sampling distribution, where now that's given as the square root of p hat q hat over n. So I've copied that down here. Here it is split up. Here I'm just substituting those values in and calculating and rounding to get 0.5204 up to 0.5916. So looking back at the problem, I can see I've forgotten to calculate the margin of error individually. That's this term right here. We calculate that as 0.0356. And we check our work. Okay, so I hope this has been helpful to you, and good luck with your studies.